Hello everyone, welcome to this video. In this video, we are going to learn one important theorem related to this chapter, linear algebra, that is Cayley-Hamilton theorem. In this video, later on we will see that how you can tackle constants related to this theorem, Cayley-Hamilton theorem. It is an important theorem for calculation of the higher power of the matrices. So without wasting our time, let's start this video. So what does Cayley-Hamilton theorem imply? Cayley-Hamilton theorem firstly implies that every square matrix satisfies its own characteristic equation. So let's write every square matrix satisfies its own characteristic equation. That means let's say a matrix A of order 2 cross 2, that is a square matrix. So let's say matrix A that is 2 cross 2, so 4 entries over here. Let's get arbitrary entries in this matrix, that is let's say 5, 0, 7 and 1. So what is the diagonal elements, sum of diagonal elements, that is trace of the matrix. So trace of A, sum of diagonal elements. What are the diagonal elements? In each video we discuss the diagonal elements in which row number and column numbers are equal. That means this element in which first row first column, and this element that is second row second column. Row number and column numbers has to be equal. Okay, so 5 plus 1, that is 6. So trace is 6, and determinant of A, that is a representative number of square matrix, that is 5 multiplied by 1 minus 7 multiplied by 0. So determinant of A is 5. So that means its characteristic equation would be, what are the roots of characteristic equation, that are going to be called as eigenvalues, and sum of eigenvalues is the trace of matrix, and product of eigenvalues is the determinant of the matrix. In our previous video we discussed this thing also. If you have not watched, then particularly watch this video. So lambda 1 plus lambda 2, that is two eigenvalues of this equation. So sum of eigenvalue would be the trace of the matrix, that is 5 plus 1, that is will be 6. So and product of eigenvalues, that will be going to be determinant of it, that is going to be 5. So if sum of roots are 6 and product of roots are 5, let's get the quadratic equation of these roots. You can find this quadratic equation by the x square minus sum of roots into x plus product of roots equal to 0 in your basic 10th level class. So x square, without wasting our time, let's write this, that x square minus, so you can write in place of x lambda, so lambda square minus sum of these roots, that is 6 into lambda, plus product of this root, that is 5, equals 0. Okay, so it is the characteristic equation of this matrix, and characteristic equation means determinant of A minus lambda I equals 0. Determinant of A minus lambda equals 0, where I is the same order of identity matrix. So it is the short technique, that lambda square minus sum of eigenvalues, that is trace of the matrix into lambda plus product of eigenvalues equals 0. Product of eigenvalues means determinant of the square matrix. So it is the characteristic equation. So this matrix, this square matrix satisfies its own characteristic equation, means that in place of lambda you will write A. In place of lambda you will write A. So lambda satisfies A, or A satisfies lambda. So A square minus 6 times A plus 5 times, there is nothing, means 5 multiplied 1, and 1 is equivalent to identity matrix, you know. That means 5 into identity matrix is a null matrix. 0 means null matrix. Null matrix is represented by this square, and under this it is 0. So okay, so it is the thing that every square matrix satisfies its own characteristic equation. Now let's get the other concept. Let's remove this one. So the next thing is, if you would someone tells you that A is some type of matrix like 5, 0, 7, 1, that type of matrix. So okay, so if someone tells you to find that A raised to power 100, let's say 100, so you will be saying that A into A into A into A into up to 100, that will be very bit difficult for us, because we cannot calculate 100 times, we cannot multiply it 100 times, that is practically impossible. But if you, let's say A square, A cube, a raised to power 4 and until a raised to power 7. That is quite possible, but a raised to power 100, a raised to power 1000, that is not possible practically. For our humanly not possible to multiply it up to 100 times. So what will be the we will be like dependent on this Cayley-Hamilton theorem, how we can determine this value. So you can write a raised to power n. Let's say n, generalize, let's generalize. So n is the power of the matrix that is to be determined. So a raised to power n, that is that can be written as c1 into a plus c2 into I. Okay. Basically the eigenvalue, let's say the eigenvalue of this matrix are lambda 1 and lambda 2. In general lambda, let's say. So lambda, if lambda becomes the eigenvalue, then the equation satisfies, the equation is valid according to Cayley-Hamilton theorem, that lambda power n equals c1 lambda plus 1 plus c2, sorry, plus c2. So c1, where c1 and c2 are constants, you have to find these constants by using two equations and two variables. Using two equation and two variable, by any method you can find this c1 and c2. So if lambda satisfies this equation, then obviously the matrix satisfies this equation. As I have told in the previous point, a point, that every square matrix satisfies its own characteristic equation. Whatever will be the eigenvalue, you can write matrix in place of eigenvalue. So in place of lambda, we are going to write a. Okay. So let's say their eigenvalues are lambda 1 and lambda 2. These are the eigenvalues of these matrices, this matrix A. So lambda 1 and lambda 2 satisfies this whole equation. So lambda 1 power n will be c1 lambda 1 plus c2, and lambda 2 power n would be c1 lambda 2 plus c2. You know what is lambda 1, you know what is lambda 2. By this equation, two equation and two variable, you are going to find the two constants c1 and c2. You are going to find. That means then the matrix satisfies this equation. That means a power n will be c1a plus c2 into 1. 1 is equivalent to identity matrix. So you know c1, you know c2, you know what is a, you know what is I. So by this method you can find a power n, where n is very big number or very small number. It can be calculated by using this theorem. So let's give an example. Like in this matrix, let's say we have to determine the power of the matrix, that is 100, a power 100, a raised to power 100. So let's apply Cayley-Hamilton theorem. Without Cayley-Hamilton theorem you cannot find, because they multiplied by n, that is not possible, right? So sum of eigenvalues, that is, so what is the characteristic equation, that is lambda square minus trace of this matrix. Trace of matrix is 6 lambda plus determinant, that is 5, equals 0. So lambda square minus 5 lambda minus lambda plus 5 equals 0. Okay. So lambda times lambda minus 5 minus lambda minus 5 equals 0. So lambda minus 5 multiplied by lambda minus 1 equals 0. So lambda equals 1 or lambda equals 5. Right? So 1 and 5 are the eigenvalues of this matrix, the square matrix of order 2 cross 2. So by using Cayley-Hamilton theorem, we can write what we can write. That is lambda power n is c1 lambda plus c2 lambda. In our previous point we discussed this, right? So in place of lambda, you will put in 1 at a time and 5 at a time. So let's apply. So 1, that means lambda 1 equals 1. So 1 power n, that is 1, equals c1 into 1 plus c2. That means c1 plus c2 equals 1. This is our first equation. This is our first equation. Now let's put 5 over here. So what is n? 100. Because we have to calculate the a power 100 raised to power 100. So 5 power 100 equals 5c1 plus c2. Now you have two equation and two unknown. Now two equation, two unknown can be solved using, let's say, 2 minus 1. So 2 minus 1. So that means 5c1 minus, that means 4c1 equals 5 power 100 minus 1. So what is c1? 5 power 100 minus 1 by 4. That is c1. Let's erase this one. Now c1 we have calculated. Now c2 is 1 minus c1. 1 minus c1 means 1 minus 5 power 100 minus 1 by 4. That means 4 into 4 minus 5 power 100 plus 1. That means 5 minus